Okay, so for the next 30 minutes or so, I'd like to focus on a particular interest that I've had for quite a few years, actually, which is carving terrain maps. So that's getting hold of data that comes directly from scientific instrumentation or satellite imagery and carving it into materials. Everybody loves maps, and I just think that this is a great sort of a class of project. If you've not had a go at something like this, it really is very rewarding. So I want to start by talking about the different sorts of terrain data types that are out there, because this is the main stumbling block for people, I think, when they first get into it. There's a lot of data out there. It appears to be in very radically different formats, and indeed it is in radically different formats. And sometimes it's quite hard to firstly pick which is going to be the best option. And then even if you do pick the best option, how do you manipulate it to get the best result? So the first thing and the easiest thing is if you can get hold of an STL or an OBJ file. So earlier in one of my earlier presentations, we talked about importing models from third-party kind of libraries and stuff. And there are terrain models out there as triangle meshes. And if you can get hold of the particular area that you're interested in as a triangle mesh, then that is actually one of the simplest ways to bring the data in. There are downsides, which we'll talk about as we go along. But that is the simplest. The next, probably commonest form is the digital elevation model. And to be honest, this data structure, which is the kind of geologists and geographers underlying scientific data format, is probably the one in which actually all the other model types are derived ultimately. So it's the form that was the original earliest shared file format for people dealing with this sort of data. And so these models still persist, and they've been around for a decade or more. And again, we'll take a look at what we can do with those. Then we're going to look at simple grayscale images. So we can get quite a long way simply by using our Aspire's image to component import filter. So we'll look at that and then finish off with a particular form of grayscale image, which gives us the kind of the best of both worlds, which is called the GeoTIFF file. So I'll point you in the direction of a few really key resources online that are good in this particular area. So before we go any further, I've said that the mesh is the best thing, or at least the simplest thing, if you can get hold of the area that you're after. And so it's worth pointing you at this relatively new website that popped up and at least I became aware of it in the last few months. It's called topo.io. And essentially it's a very, very clean interface. And it's primarily aimed, I think, at people wanting to do 3D printing, as often is the case these days. But what it will do is use a Google-like search term to find and recover the data in a standard tile size and bring that down, convert it to an STL, and let you download the STL model. In fact, I think it's an OBJ model. It's a very simple interface. That's really the best thing about it. It is an OBJ file, so you get a 3D model, which we can import through our standard model import method. The only downside I found is in playing with it, it was very exciting when I first got a link to it. As I played with it more and more, and indeed in preparing for this presentation, I downloaded more and more tiles from different parts of the world. And in fact, you do get quite a lot of variability. And in fact, there was quite a few tiles, including, for example, around the Chicago region, where there's data missing from the OBJ files. It's not correctly creating a seamless mesh in all cases. But presumably these things will get fixed and it will get better. So it's definitely one to look out for. And I'm going to show you the simple process in a moment. One of the downsides generally about triangle meshes is they're usually big files. So this does result in files that are 40 meg or bigger. Not massive by modern standards, but certainly worth bearing in mind that the trade-off against detail and file size is quite poor for a triangle mesh. There's a lot of effectively wasted data in representing point heights as using triangles. They take, broadly speaking, 3 times as much data. So let's have a look, dive straight into a demo and see if we can't get that model into Aspire. Okay, so let's take a look at how we might use topo.io, which is the site that I mentioned in the beginning of this presentation. So this is a relatively new site, and it's kind of still, I think, going to likely change. It's a lovely interface, so it's twiddleable. Comes up with this model straight away that we can get at. You can move around a little bit by clicking these little arrows to move the tile around. And you can also crucially type in a straightforward plain English search. So here we can get hold of the Alps take a look at that. We can kind of adjust the scaling of the height, but since we can do that ourselves anyway, we're not too worried about that. And you've got various zoom levels to play with to get hold of broader or less broad regions of data. So let's grab this one. If I just do save the 3D file now, that's it. I click the button and it starts to download as a model.obj file. And that means now we can cut across to Aspire. I'm just going to create a blank new project to work with. And then in the modeling tab here, and of course this would work in VCarve as well. So VCarve Pro now has the ability to import a 3D model. We can get hold of the Topo model like so. It's quite a big file. Like I said, they're about 40 plus 50 meg. It takes a little while, and in it comes. And now we can do the usual kind of system of importing a model. Typically, we're going to use front to bring it aligned with our object. And since I know this was 150 square, we can actually match that exactly, like so. You can use, obviously, the our zero plane here to slice away any bit of the terrain that you don't want. So that's quite handy. So you can reduce the unused Z level. And basically, once you're happy, we discard below the zero plane, click OK, and there's our terrain model. I turn on our shadow shading, makes it pop a little bit. It really is as simple as that to get hold of your first terrain model out of Topo. Okay, so that's the process for a simple STL model where all the work's been done for us by a website. But of course, the problem here is that you can't always get the data that you're after, and you certainly can't quite tile it up in the way that you might want for a very, very specific job. So let's go to the next file type, which is the digital elevation model, or DEM file. And this really is cutting to the kind of source, because most, as I say, of these other peripheral processes are starting with this data. And in fact, we can start with this data too. It is primarily the standardized form to represent satellite and scientific data amongst the scientific community, and has been around, as I said, for sort of more than a decade. There's some great stuff out there that you can get hold of, including NASA's data for the Moon and Mars and even other planets. So that's kind of interesting. I did a model at one point of Olympus Mons, the enormous volcano on the surface of Mars. The file formats themselves are relatively simple from a structural point of view. They are in fact just ASCII text files with a fairly simple header, data and footer structure, so they're quite easy to deal with, but they're scientific, and so that, although that encoding is straightforward, the content can be quite fiendish because it's dealing with data that is effectively flattened versions of global data. We have a really useful gadget, the regular grid importer, which you can get from gadgets.vectric.com. It's the free download. And this, not everyone knows this, but one of the types of data that comes in this regular grid format is the DEM file. And so it will import DEM files, most DEM files very effectively. So let's go and see that in action. And as I said, it's often really interesting data that you can get in this DEM file format. On the this Washington Education site, there's actually a nice bit of work somebody's done to kind of sort out the data that was available for Mount St. Helens before and after the eruption in 1980. And so this is quite a fascinating file to get hold of and work with. So let's cut back to the software now and have a look about how we might get that data into Aspire. Okay, so before we can go ahead and use DEM files, we really need to make our way over to the Vectric gadgets store. So that's at gadgets.vectric.com. And once you're there, you can scroll down and have a look in the gadget library. So these are little plugins for Aspire. And in there, you'll find a regular grid importer. And this gadget essentially takes regular, as the name suggests, data in a text file that's in a regular form, and it converts it into a 3D component for us. And that happens to work for DEM files. You can actually get hold of the St. Helens DEM files from here. I also have put the source location that I got them from. But download this gadget, and then, so you can just download the gadget here, come back to Aspire, and then you can install a new gadget like so. Just browse to the gadget you've downloaded, double click it, and it will install for you. Okay, so once you've got that installed, you can go ahead and create a new file, and on the gadgets menu, there'll be a new entry here called regular grid importer. If you select the regular grid importer, now it'll offer you the option to open up that DEM file. So let's go and get the Mount St. Helens. Let's get the before the eruption file and just open that. It's very quick, so it's converted that into a component for us, 3D component you can see here. And let's do the other one. Now, because the data was taken obviously at different times, it's actually slightly different resolutions. So the quality of the data the second time round was substantially better. So they've come in with slightly different sizes because there's just more data here than here. But we can correct that size. We can just find the size of this one, which is 118.5 millimeters. I'll just copy that. And let's scale this one up to be the same size. And I don't want it to scale the Z values when it does this. Apply that. Now what we should find is that they're both a similar size to one another, so we can put them side by side and take a look in the 3D view at the comparison. So before and after the eruption. So you can see the data is really good. It's a really interesting view of quite how catastrophic that really was in 1980. But even perhaps more interestingly, we can do something quite unique, I think, probably. So if I take the before and the after and I put them over the top of one another, and then we subtract the after from the before, we get an interesting effect. We take away everything that matches and we're left with the difference. So what you're seeing now effectively is the mountain that disappeared. So all of this material was blown away in that eruption. So it's quite a cool way of visualizing that event in a unique way. Okay, so that's basically how to do DEM files through the regular grid importer. Okay, so hopefully that demo got you quite interested in the nature of this data and what sort of fun things you can do with it. But let's now, unfortunately, get into a little bit of the ugly truth about some aspects of DEM files. The first thing is that the format is not as standard as it might be. There was a variety of little apps and things that came out to render DEM files, and they kind of abuse the file format a little bit. So there's some binary variants that you find that we can't really deal with. The biggest problem is that the data quality is quite variable because the DEM files themselves don't determine the data source. They're just a formatting method. And so that data can come from LiDAR, from the space shuttle satellite missions. And it's the globe is covered with very variable quality of coverage, and so your DEM files can be quite variable. So that's one issue, but unfortunately that's just the nature of the data, full stop. More of a problem is that there's gaps and holes in it. So often if you get hold of files that have been processed a little bit, one of the things that person will have done on your behalf is fill in any gaps and holes that appear in the data. And they can literally just be little patches where reflectivity was peculiar, or they're just missing a section, a strip. And you will need to kind of sort those things out yourself. The upside is that Aspire is pretty good at it. And I shall show you as well, if you do a little bit of editing before you import into Aspire, you can get around a lot of these problems. Also, the raw tiles of data, as I say, it's kind of a geospatial kind of representation. So there's a lot of scientific terminology, and you have to think about arc seconds and degrees of coverage and all that sort of stuff. So sometimes getting hold of those raw tiles of data for the region that you're interested in is a little bit awkward. The tiles may not overlap quite, or they may in fact come from different data sources, and the region that you're looking for might unfortunately fall between the seams or between the cracks or on the seams of different data types, which needs to be sorted out. So those are the sort of downsides of DEM files. On the upside, some of you will know Paul Roundtree, who's a contributor to our gadgets, and he's actually written quite a mature product now. It's been around for quite a few years off his website, paulroundtreeweebly.com. Here you can go and have a look at his gadgets, and in particular he's written a couple of little apps that take those DEM files in and do an STL conversion for you, allowing you to fill in data in your kind of areas and location data in a kind of friendlier way. So take a look at that. And he just asks for a donation if you make use of it. But it can be quite handy for kind of wrangling the raw dem file data into a more usable front end there. So they're called Topo and Big Topo, his second one. Okay, so the next thing I want to talk about is just grayscale images in general. So this is using image import as opposed to raw data or 3D model import to get hold of 3D data. And you just have to be very careful, and we have to be clear, and this slide is intended to clear up a big misconception that occurs quite often, which is the difference between just a grayscale image and a true height map. So what I'm meaning by the grayscale images in this case is images in which the brightness is directly related to a height. So if a pixel on the image is white, it means it's very high. If a pixel on the image is black, it means it's simply low. As opposed to these images on the right-hand side here, which kind of at first glance look like they might be useful. But if you look again, you'll see that these images are both lit from the top left corner. So what you're really getting is grayscale showing shading, shadow and brightness, and not direct height data. And so quite often this sort of image, the correct sort, where there's a direct mapping, is used to create this sort of rendering, which is easier for the human eye to interpret. But the ones that we need are like this. Okay, so you need to be looking at images that look a little bit like this kind of X-ray scan of a brain or something. That's the look you're after. If it looks like this, I'm afraid it's not going to be very useful to us. You're not going to be able to bring in that data directly. On the plus side, though, it's not just terrain, right? So once you get into grayscale images, and I'm going to digress here a little bit off my core topic of terrain, just to point out, because I think it's a kind of often missed area of easy to get hold of models. People create these grayscale images in all sorts of ways, in paint packages, using airbrushes, as well as it's the format that a lot of laser machines use for 3D lasering. So if you actually search Google for grayscale height maps, and you can spell grayscale either the American way or the English way, sorry about this, you're going to see this throughout my slides, then you will find that there's a ton of this stuff out there. Obviously, the normal copyright issues apply, so be careful when you take a model or you're looking to use a model that you obey and follow the correct approach for that person's work. And obviously, they have some of these images you can see have required an awful lot of work to achieve. But there's plenty of material out there if you get into it. So I think it's worth just having a quick digression at this point to talk about these grayscale images, terrain and other data, how we get this into Aspire, maintaining the maximum quality. So the important thing here is when you bring in this image, do it directly from the component to bitmap conversion. Don't bring in an image, click the image from within Aspire and then create a component from it. And the reason for that is if we import images in general, by default, we are processing them automatically to improve the tracing behavior. And we do that by effectively color reducing those images so that the regions that you're likely to want to trace are more easily found for kind of V-carving. If you're not going to use it for that, for tracing and V-carving or toolpathing directly, you actually want to use it for component creation. You want to avoid that step. And the way we allow you to avoid that step is to import the component directly. So I will emphasize this in a short demo in a second because it's so important that I think it's worth showing it. Another thing to point out is a lot of these images will be online in various image file formats. And if there's a lot of compression formats out there that are really good at fooling the eye. So they're really good at capturing light and dark information in such a way that your eye doesn't miss the bits that they've removed to compress the image. But what you will find is that they suddenly appear again when you try and convert that image into a 3D model. And you tend to see it in the form of a strange sort of weave texture that appears over your image. So my tip there really is that you want to kind of avoid heavily compressed JPEG images in particular, which are really common on the web. And if you can find a PNG equivalent, usually that will give you a better result. PNGs are also compressed, but the compression algorithm used in most PNGs is just a little bit less intrusive and produces fewer artifacts for us when we bring them in for this process. So find the image you're after, but then see if you can get a PNG of it. Okay, so let's whiz across the software again and see about importing a grayscale image to maintain the maximum resolution that we can.
Okay, so this is a very fast demo because we just want to take a quick look at how one brings in a grayscale image such that it maintains the data at its best possible quality. And there really just is one very quick tip which I will show you. So I'm going to create a blank model as previously. And then what we're going to do, instead of loading our image as you might imagine through the image load here, import a bitmap. Notice for tracing, crucially, we don't want it for tracing and we don't want it to do any previous processing that helps with the tracing process. So instead, I'm going to the modeling tab, and here we can have create a component from the selected or imported bitmap, and that's the crucial thing. If you click this button when you have an existing image, it will do the conversion from the selected image within Aspire. But since we don't have a selected image within Aspire right now, so we have no images at all, it offers you the option to import instead. Now the important thing here is that this importing process will not go through that tracing filter that we do to improve tracing, and it keeps things therefore at a higher quality. So let's find ourselves in our terrain. So cheekily, of course, this isn't really terrain. These are just examples of JPEG images that I found online by typing in grayscale height map and downloading them. So let's bring in this tiger, and as quickly as that, I can bring it in, and it's converted everywhere. Let's put the two images side by side, which is that way around, it's better, isn't it? Everywhere that is bright in that image, bright white, is high, and everywhere that's black is low, and you can get a feel for the model that results from that. I'm trying to not twiddle it, let's do that. And let's turn on our shadow shading, makes things pop a little bit better. So you can see it's pretty good, right? So you get some artifacts in here. I was mentioning about the compression artifacts. This is a JPEG image. And so these funny little grid areas, while you've struggled to see them with your naked eye in the image, they really come out here in the transformation of that image into a 3D model. So you might need a little bit of processing here, but what's really good is our sculpting tools are excellent for fixing this stuff up. And so you might well find that this is a really good source, additional source of 3D models that you hadn't previously considered.
Okay, so strictly speaking, of course, that was a bit of a digression from terrain to talk about grayscale images in general, but hopefully you still thought it was useful. Let's get back into now where this fits into my terrain discussion. Well, what I really want to get to is the last file format I want to discuss in this presentation, which is the GeoTIFF file. So as the name suggests, some of you will be aware that TIFF is an image file format that we support, the tagged image file format, and a GeoTIFF is a special form of that, which includes additional tags to the normal image tags relating to geospatial data. It's an alternative to a DEM file, but often the source data is the same. So all those issues I raised about DEM files to do with data coverage of the Earth and gaps and things, I'm afraid they still will all apply, because you're going to be working with source data effectively. They're a standard-ish representation like the DEM file, and I say ish because they can have more or less data in them, and people still, one of the best things about the tagged image file format is you can have whatever tags you like, and one of the worst things about it is you can have whatever tags you like. So although it's a standard file format, the tags that can be in that file can be quite variable. The upside, though, is that we can just ignore tags we don't know about. So generally speaking, what this means is this is kind of like a DEM file that we can use our normal image importing for. So it has the upsides of a DEM file without having to have a separate import filter or dealing with a gadget to get the data in. So that makes it a robust way to get the data into Aspire. The only downside is, like DEMs, it's difficult to get the data. Right? Where do you go and get this data? Well, again, what prompted this talk is a relatively new service offered now by the USGS, which really kind of massively improves the user interface element of getting hold of the data for the region you're interested in. So I'll put the link up here, Earth Explorer, and really it's an amalgamation that kind of consolidates all the data into a single interface so that you can use like a Google map to literally draw a region or type in a Google search or just scroll around it with the mouse, and then you will get down what data is available in the consistent GeoTIFF file format across the board. So it's really, really helpful for us because we can then just generally deal with the GeoTIFF in a very similar way to the demo I just did for a grayscale. Okay, so let's see if we can get hold of this data set as a GeoTIFF file, and it's a data region here of the Salzkammergut region in Austria, which is effectively there, the Austrian lake region here, and a little bit of Bavaria, and the beginnings of the Austrian Alps down to the south here. It's a nice crinkly bit of texture to have a look at. So let's cut across the software and show the process of getting a GeoTIFF file in.
Okay, so in this demo, I want to show how we can grab a GeoTIFF file using the nice Earth Explorer interface, fix up the data if we need to, which you may not need to, but I want to highlight at least two areas you probably will encounter if you do anything beyond the most sort of basic searches, and then bring that data in and get a really good model out of it. So I'm going to cut across to the Earth Explorer, which is this site offered by USGS. So that's earthexplorer.usgs.gov. It's a really nice kind of main interface here is basically Google Maps. So they've used Google Maps to allow you to pick the region that you're interested in. And you can just type in a Google Map search here. You can also just take an area using a polygon or a point. So you can just click on the map, put a push pin in, or you can use the polygon button here, and that allows you to effectively region an area by defining points like so. So essentially this is a really, really good way of at least narrowing your search down to the bit of the globe that you're interested in. Once you've done that, you can go on to the data sets that are available. And from our perspective, the ones that are going to be really important for us are these digital elevation models, so the digital elevation maps, because those are the ones where there's point heights. There's all sorts of other stuff here for people looking at water sheds and aerial imagery, etc. But in here are the key data, scientific data sets and satellite data sets that offer us heights. The DEM suffix you'll be familiar with now by this tool, which is the digital elevation model file formats. And this allows you to see their coverage on the map, because as I was saying to you before, the different data sets only cover certain regions, and so depending on where you're interested in, you may or may not be able to get the region that you're after. So this allows you to overlay it over a real map that you can see and understand more clearly which regions are covered and which are not. So select the file, the data set that's closest to where you're interested in. You're going to select more than one, and then go on to download those data sets. At that point, you will need to create an account to get the downloads, but it's a very quick process, and once you've got an account you can reuse it, and the data itself is it's got variable usage policies, so you need to make sure that you are obeying the usage policies, but most of it is quite free to use. Once you've done that, you'll end up with a folder like I've got, a zip file with the region that you downloaded. In this case, I've downloaded that region of the Austrian Alps, and they've come in as image files, and they are obviously image files because Windows has created picture thumbnails for them automatically, and they have the suffix here of a TIFF file. Now the thing is, it looks very black, which is a bit unexpected. So let's find out what happens when we actually create a model and import that image in the same way we imported the grayscale previously. So this time around, we're going to go into the GeoTIFF file and bring in this TIFF file as it comes down from the website. I should point out, actually, let's just whiz back to this for a second. You'll get them in the same structure as this. You get a little README telling you what the structure is, but essentially one of the TIFF files is just dem.tiff and the other is num.tiff. Now this one is actually, from a scientific sort of nerd's point of view, this is actually an image that shows the confidence that the data matching points in this image are correct. And it is interesting actually, because you see some blobs here that are telling us that there might be some errors in the data around about here. So just remember that, because in a minute we're going to see that that is exactly right and we have some trouble with it. So this one is effectively error codes for the main one. So make sure you open the correct one. Anyway, we're going to open the correct one, which is the dem file, not the num file. And it's sort of massive. Let's shrink it down to the appropriate size for my job, which was, I think, 150 mil. F9 brings it to the center of the model. And we can start to see the data. Let's have a quick look at this data. So it looks very disappointingly, I mean, it's definitely terrain data, right? But it's very plateaued, which is very disappointing, and it's very flat. So let's come in here and have a look if we can't scale it. But it says it's 18 mil high. That doesn't look right? But when I twiddle this, we can see why. And as I pointed out, there was that little bit of, we all had the indication from the error map that was going to be a problem. And sure enough, there's some holes in this. In this particular case, there's a spike of data there, which is clearly erroneous. So we can fix that before we go any further. And as I said, we're quite good for these sort of things. So we can go into the sculpting tool, for example, here, just fine it. And what I'll do is I'll make it lower only and smooth it out. And we can kind of just smooth that region, but only smoothing downwards. And that's quite a neat way of removing some of this stuff without damaging the surrounding area too much. That looks better. Let's have a look what we think the height is now. We think it is only 0.9, so that seems much more likely. Let's grow it to 5 mil and take a look. So that's kind of much more what we'd like to cut, say 6. And you can see that it's kind of looking very plateauy. The reason it's looking plateauy when we look at the grayscale is you can see that we've got a limited number of grayscales. It lurches from these relatively crude brightness patches very, very quickly. Instead of it being a smooth gradient, we've got stepped gradients here. So what's causing that? Well, the problem we've got is that most of the height data here, in terms of the Earth as a whole, is only variable by about 1,000 meters or a few thousand feet. And so the data in its raw scientific form is all crammed down the lower end of the range. And so we're only using a few shades of grey to deal with the range of heights that the vast majority of the mountains are actually in. So this is a big problem for us. Can we do better? Let's see if we can do better. So let's get rid of that one. I'm going to go back, just take a look again at this image. So the problem is, can we actually shift the heights to cover a broader grayscale? And I'm going to use an image processing package here called GNU Image Manipulation Program, or GIMP for short, rather unfortunately named. It's a free download, and one of the cool things about it is it will handle these 16-bit grayscales natively. So it's really handy for that. So I can open exactly the same file in here, and we see the same effects, including that spike, look, which is now a bright blob. But you can't see any of the terrain because it's all spread down the lower end. Luckily for us, this does have an interesting filter here, which allows us to look at the color levels in this image. And when I pop that up, this graph here looks very technical, but really what it's showing us is that the vast majority of all the data is down in these areas of grey to very dark, from black to very dark grey. And so we're not using any of this grayscale to actually represent the data. There's a very cool button here, which basically is our savior, which is to auto level the inputs. So we can sort of manipulate this. There's lots of sophisticated ways of manipulating this, but this is a kind of magic button as far as we're concerned. And what that does is spread the data across the full range instead of only using the bottom end like so. And with that done, suddenly the whole thing pops back to life. And if I save this file off again now as a duplicate, so I have to export it as a TIFF file. So export as a TIFF file. This time we'll call it leveled dem. And export that. We'll just use the default settings, basically no compression, and go back to Aspire. Let's do the same process we did before. Remember, we want to load it directly as an imported bitmap. Now we can see that even the thumbnail is looking a lot better. Size it to our model again, 150, like so. F9 brings it in. And let's take a look, and whoa, what a difference. Okay, so now what we have is a really impressive model. We can take the grayscale levels down a bit. So let's take them down to 6 mil where we were before. Obviously, really, you could sort of cut these things as accurate heights, but what you'll probably find is really surprising how much you need to accentuate the grayscale for a model that looks good. you actually need to use probably 3 or 4 times scale factor in the Z to pick this up. But here we can see the lakes of the Salzkammergut region of Austria and the beginnings of the ski areas around here. I believe, let's think, so this is Salzburg up here, and down here is Berchtesgaden, I think, around about the Bavarian Alps, around about this region. But you can see it's a really interesting model. The sharper ones amongst you as well will have spotted that it kind of fixed that glitch too. So that auto leveling was really handy because it took that glitch out. It is kind of there in the data structure. If you look very carefully, there's a sort of bit of a blob here, which is where it was, I think. Or no, actually here it is. Sorry, it's here. But essentially, you notice it now because it's been leveled out, and that's a pretty good terrain map. Okay, so that's covered quite a few issues, but really how to get that DEM file down from the site, sort it out, and bring it in.
Okay, so hopefully what you saw in that demo was it's a pretty cool, high detailed way of getting the data in. But it was important, as you could see, that we scaled that data correctly so that we could maximize the resolution as we came in. So that's really my big tip about the GeoTIFF file, is it's true 16-bit height values, which means that they are genuinely giving you meters. And sometimes that means actually we're going to very poorly utilize the available range of grayscale for our usage. So that means really you want to auto level that brightness so that you spread the actual range of the data that you're getting completely across the available grayscale. Otherwise, you'll see the effect that we just went through. You can also deal with the holes and gaps. And as we saw in that demo, the auto level also resolved a problem we had with a rogue kind of region in the data. So it's a really handy way of doing that. And if you just pre-process that file, it's a 1-second thing. And once you get into it, you realize it's really straightforward. You get a really good result out. The demonstration I just did was using the GNU image manipulation program, which is, questionably called GIMP. It's a free and very, very powerful editor. It's not the most user-friendly. I can't pretend it is, but it does have the important quality that it can deal with 16-bit grayscale images and maintain their 16-bit resolution without having to convert them. You can often load TIFF files in, and in fact, in the same way that we do in Aspire, you can load these grayscale TIFF files in, but once they're in, you tend to lose the 16-bit range because they get dropped back down to 256 levels. So the GIMP's cool for that because you can edit it in it. Plus, it is free, so it's a really handy bit of kit to have in your armory. So that you can go and download that from gimp.org and make use of it, even if you just use it for this particular task. Okay, then, so that brings us really to the summary for this talk. And I just want to whiz through what we've covered. We've looked at triangle mesh models, and we've talked about the strengths and weaknesses of each of these types. In the mesh model situation here, the problem is, although they're robust, and they can be big, and they're ultimately derived from the same DEM data. And so while often people will have fixed a few of the issues for you, you have to just get what you're given. So that you can't always get the area that you're after. The grayscale images, they were really simple. And if you can find what you need, you can really make good use of grayscale images, but you need to make sure it is actually a height map and not just a shaded grey image. The DEM files we looked at, that's really getting right down to the scientific source of a lot of the other file formats. But you probably need a helper app of some sort to get hold of the data you're after, because it's quite difficult unless you're pretty familiar with latitude and longitude, or the world divided into degrees and arcseconds. Then you're going to find it quite difficult to locate the area you're interested in. And then I finished talking about the GeoTIFF file, which kind of is the current best of both worlds, I think. It holds the data in a format and a resolution that's equivalent to a DEM file. It's quite an efficient file format, so you get, although they're big files, those big files can hold an awful lot of really high quality imagery. And there's this new interface available now, Earth Explorer, which really, really simplifies the process of getting down the files that you're after from the different data sources that are available. My only caveat there, of course, is that you probably do need to do a little bit of editing to get the best from it. Okay, and that brings to an end my presentation here on getting amongst carving some terrain data. But I really do recommend it. They're really visually interesting and cool projects to do.